This is the final video for implicit differentiation. This is implicit differentiation part 5. So this is one other way you'll see where we can take our dy dx's and then solve for different kinds of problems. So this says, consider the curve that's given. Is it possible for this curve to have a horizontal tangent at points where it intersects the x-axis? Find all points x, y on the curve that satisfies these conditions, or explain why they do not exist. So let's go ahead and interpret what this means. So the first thing is horizontal tangent, and from our previous lesson, a horizontal tangent is when dy dx is equal to 0, which means we need to set our numerator equal to 0. So that's one part. The second part is it has to intersect the x-axis. So if we take a look at what that means, the x-axis, doesn't that mean I want to take a look at this horizontal axis right here? So we need to see if this is possible. So let's go ahead and find our dy dx and see where there is a horizontal tangent. So let's take our derivative, 3x squared plus 2y dy dx, since this is a y, right? Then I see I have the product rule. The first term times the derivative of y is dy dx, plus the second term y times the derivative of the first is negative 2x equal to 0. And if I collect my terms and move things over, I'm going to move this over here and this over here as well. So if I clean it up, I get 2y dy dx minus x squared dy dx is equal to, that's a negative, so on this side it's a positive. So I get 2xy. I'm going to put these in alphabetical order. And if I move this, I get minus 3x squared. And just like we normally do, once I get this, I'm going to need to factor and then divide. So I'm going to pull out a 2y and an x squared. And then x squared. And get dy dx on the outside equal to 2xy minus 3x squared. And like we said, divide by what I factored, 2y minus x squared. These cancel. And finally, I get dy dx is equal to 2xy minus 3x squared over 2y minus x squared. Okay, so now that we have our dy dx, what we're going to want to do is set our numerator, which is highlighted here in green, equal to 0 to show I have the horizontal tangent line. So I'm going to take 2xy minus 3x squared set equal to 0. The only thing I can factor out here is an x. So I'm going to do x times 2y minus 3x is equal to 0. So that means x is equal to 0, or 2y minus 3x is equal to 0. And if I solve for x again, I'm going to get negative 3x is equal to negative 2y. Divide by negative 3. These cancel, and I get x is equal to 2y over 3. So let's check and see if those conditions work. According to this, if I'm hitting the x-axis, that means my y has to be equal to 0. Well, if my y is equal to 0, and I have to take a look at these and see what happens. Well, if x is equal to 0 and y is equal to 0, if I plug it into the original equation, I get 0 plus 0 minus 0 is equal to 9. Well, is 0 ever equal to 9? No, so this does not exist. This will not occur. Let's take a look at here. Well, it says if x is equal to 2y over 3, and we are told y has to equal to 0, doesn't that mean x is equal to 2 times 0 divided by 3, which is equal to 0? Wouldn't that give me the same exact problem as here? So to answer this question, let me see how I could write this down. I can say that no point exists to have a horizontal tangent line that intersects the x-axis. Okay? So let's take a look at the next problem and see what it says. It says, is it possible for this curve to have a horizontal tangent at points where it intersects the y-axis? So just like we did earlier, I need a horizontal tangent, but now I need it to hit the y-axis. So horizontal tangent's the same. I need the numerator to equal 0, and we already did that. So we had 2xy minus 3x squared equal to 0, right? Now it says I need the y-axis to intersect. So if I have the y-axis intersecting, which is this one right here, that means my x has to equal 0. So we already factored this earlier, and when we factored it, we had x is equal to 0, or we also had, let me go back to our answer here. We also had, where to go? X is equal to 2y over 3. That, or we said x is equal to 2y over 3. Well, if x is 0, we want to check what happens to this. And we can already cross this one out because we already said that if x is 0, y is equal to 0, but we knew that failed. So we're not going to worry about that. We're now going to just take a look at this x is equal to 0. So we're going to plug this into the original equation, and we get 0 cubed plus y squared minus 0 times y is equal to 9. Well, these zeros are going to cancel, and we get y squared is equal to 9. How do I undo a square? Good, I need to square root it. So I get y is equal to plus n minus 3. So what we need to do is make sure this works. We actually have 2 points now. When x is 0, positive 3, and when x is 0, y is negative 3. So let's plug this in to make sure that it works out. And if it works out, that means we will have horizontal tangent lines that intersect the y-axis. So let's check it with the blue one. I get 0 cubed plus 3 squared minus 0 squared times 3 is equal to 9. This and this cancel, and 3 squared is equal to 9, which is equal to 9. So I know this one is correct. I can check it with this problem now. I should have used a different color. So let's split this, and I'm going to write this one in green. So I get 0 cubed plus negative 3 squared minus 0 squared times negative 3 is equal to 9. Once again, this cancels and this cancels. Negative 3 squared is 9, which is equal to 9. So we know that this also exists. Perfect, and that's the end of our implicit differentiation problems. What I'd like you to do is to take a look at your implicit differentiation packet, so the orange packet, page 10, and I'd like you to do this as an exit slip, number 28. Okay, thank you, ladies.